Today we're going to be drawing single bonds for ionic, polar covalent, non-polar covalent, and we're going to do some metallic bonds as well. So we'll start, what I would recommend is if you're doing this on a blank sheet of paper, I would take the sheet of paper and either fold it in half twice, so that way you get 4 columns, so you can space everything out evenly, or you could literally just fold it in half and then maybe draw a dotted line down it. I spaced mine out using the computer, so it's a little bit easier. So, and also these, this version of the notes is going to be available for you to write on. So the first thing we have to do when looking at ionic compounds is we have to figure out how many valence electrons they have. Now, I included the electron configuration underneath, but you could look these up off the periodic table. I'm going to use an X and dots. It doesn't matter what you use. And now let's take a look. So this happens when the electronegativity difference is greater than 2, but it also happens when you have a metal with a non-metal. It's another way of determining if you're dealing with an ionic bond. It's actually probably it's the faster and probably more accurate way. But what ends up happening is the sodium, if we know the octet rule, wants to lose 1 to become stable. Chlorine needs to gain 1 to become stable. So sodium gives up the electron to chlorine, or you could also say chlorine takes it from sodium. That's probably more accurate. So when we're done, we get our Lewis dot diagram. Na lost the electron, so it goes +1. Chlorine gained the electron, so it goes -1. I put brackets around the element that gained it. And there's the Lewis dot diagram. Now, the reason we use the brackets is we are trying to show that that X, this one extra electron that was sodium's, now belongs to chlorine, and sodium doesn't have any claim on it, which is where the brackets come from. It's like a fence. All right, so this is called an ionic bond. It can also be called a salt. The term salt, we use it in our home, in everyday life. It gets used to talk about specifically table salt, but any ionic compound can be called a salt. It's a very general term. The electrons are transferred. The quick way of figuring out if you're dealing with a ionic compound is a metal with a non-metal, and in my previous video I went over that, how to use the periodic table to do that. And then what holds them together? Well, the thing that holds these elements together is the opposites charges attracting. It is called the electrostatic force, but that is a fancy term for saying opposites attract. So what it looks like is this. Here's my Na atom. It has a positive charge. Here's my chlorine atom. It has a negative charge. The opposites attract. And that is what's called the electrostatic force. It's a fancy term for saying opposites attract. So now let's jump to the non-polar covalent bonds, the 2 Fs. So in this situation, both Fs have 7 valence electrons. I'm going to rotate the way I put them around. So normally we say 1 dot on every side, and then you double up. And that's fine, and you'd get this if you did that. I just did the reverse direction because I already know the answer, and it's going to make showing the bond a little bit easier. So in this case, they both want to gain 1. Neither one of them has a stronger electronegativity, so it can't take it away from the other one. So instead of transfer, we get sharing. So we use a circle to show the sharing. When we clean it up, it's going to look like this. The electrons that got circled become the bond. A single line is called a single bond, obviously, if they share more than 1 pair, which we will get to in our in a couple lessons from now. I'm not exactly sure when we'll get to it, but we'll talk about double and triple bonds as well. But right now, all these are just single bonds. So this is still an intro lesson because we will eventually go to what they look like when they form more than 1 bond. So it looks like that. Now, there is another way of showing this. This is an older way. I'm going to use X's and dots for this again. The other way of doing it, instead of using a line to represent the shared electrons, and this can be done with dots, it doesn't have to be X's. I'm just switching to an X system just so I can make it a little bit more obvious. That's the alternative way of showing it. And what this means is the electrons that are shared get put between them. And then, and that's why I'm using dots and X's. And so this would be 1 bond because there's 1 pair of electrons being shared between them. If they formed a double bond, then what you'd actually see is two pairs of X's, or two pairs of X's and dots between them, and if they formed a triple bond, there'd be three pairs of them between them, and they would show it that way. If you did it with the line version, which is what everyone's going to do here, this is the modern way, this is like a very old way, it would be one line versus two lines versus three lines, so you get the idea. Next one, this is going to be the hardest of the three. This is called, oh, and then let's draw what actually holds them together. So these are called nonpolar covalent bonds. What it means is that they are sharing, that's covalent, and they're nonpolar, in other words, no poles. So there's no positive and negative end, as opposed to the next type, which will have them. The way to tell if you're dealing with this type of bond, you have two nonmetals, and they are the same element, like F2, H2, N2, you know the whole saying, Brinkelhoff. What holds them together? Attraction to the mutually shared electron. So let me show you how that works. Here's the nucleus of one F. Here's the nucleus of the other F. They are, in this case, I'm actually going to move this just so I have a little bit more space to draw the next one. So I'm just going to put it over here. So here's the nucleus of one F. There's the nucleus of the other F. I'm only going to show the electrons that they're sharing because there's only one pair. It's these two. These two that are in the circle are what I'm drawing now. There's one. There's one. And here's what happens. Here's the orbital. And the attraction is this. This nucleus is attracted to both of those electrons, and so is this nucleus. And that's what ends up holding the atoms together. The 1F nucleus doesn't want to give up the extra electron that it gained to become stable. The other F nucleus does the same thing, so they share their electrons. And now, to make this perfectly equal sharing, if you notice, my circles aren't that good, but the distance between the nucleus and the electrons in the middle should be equal on both sides, and the size of the orbital should also be equal. I tried to make them as equal as I could. Maybe you can do a better job. And then what I'll do is for the unequal sharing, I will show you, I'm going to exaggerate it and show how it's unequal using this model. So now let's go to the unequal sharing. So in this case, the electronegativity is between 1.9 and, so it's greater than 0 and it's less than 2. That's basically all we have to say. And here's the valence electron. Hydrogen has 1 valence electron. Chlorine has 7. Now, remember, this is an exception to the octet rule. Normally 3 or less we want to lose. Hydrogen is the only one that doesn't. This one has 1 valence. Hydrogen has 1 valence electron, and it wants to gain to get to 2 to look like helium, which is a noble gas. It is an exception. You do have to memorize that one. And the other logical thought is if it lost 1, it would have 0, and 0 doesn't sound like a good number of electrons to have when you're trying to become stable. So in this case, we're going to use a circle to show that they are sharing, okay? Because the reason they share is simple. Chlorine's not strong enough comparatively to hydrogen to rip it away like the ionic, and since they are unequal in terms of their electronegativity or strength, they're not going to share perfectly equal. They are going to, in fact, share unequally, and that's where we get the poles from. So the way we draw this is simple. The electrons that are in the circle become the line. Don't forget about the extra or lone paired electrons on the outside. And now the way we show the unequal sharing is this. We draw an arrow pointing towards the negative element, and we put the end of the arrow as the positive end. That shows the positive end of the molecule. So now, the reason I know it points towards chlorine is because when I look up the electronegativity of chlorine, it's 3.2. And when I look up the electronegativity of hydrogen, it is 2.2. So the reason the arrow points towards the chlorine is the negative end, and therefore the H is the positive end. And the reason the chlorine is the negative end is because it has a higher electronegativity, so it is stronger, so the electrons end up spending more time around chlorine, creating what's called a partial negative charge. Now, there is an old way of doing it, meaning the old way of drawing these is can also be shown. So the way you would do it is, it's the same exact as the other one. I'll use an X and a dot for this model. So the electrons that they shared are just put between them, so that the electrons that are circled here or in this line are these electrons here. And what they used to do is they would do this. They would use this, I believe it's a delta. It's kind of like it's like an S, but like the top is shrunk and the bottom part is enlarged. And they would use like a delta S and a negative and a positive, and then you would see this. There's either a delta or a sigma. I don't really know my Greek letters too well. So you would do that, and then this would show the negative end and the positive end. Just keep in mind the arrow, what the arrow is doing, I'll go over it one more time. The arrow is pointing towards the negative, and then that end is the positive, and that's how you know. But so when you do this on a test, you're always going to give me this version up here. The reason I'm showing you the older style is because I have seen on Regents exams specifically, sometimes they will include questions that use the older style of diagrams. It's not wrong, it's just not modern. And so that's why you don't see it a lot anymore, but I am showing it to you just in case you come across it. You know what it means. These bonds are called polar covalent bonds. The reason they're called that, covalent means they're sharing, polar means they have poles. In other words, a negative and a positive end, which result because the electrons are shared unequally, because the electronegativity is not equal. How do you tell you're dealing with this type of bond? You have two nonmetals. They are different elements. What holds them together? Well, the same thing that holds these covalents together, but instead of the electrons being perfectly square in the middle, they are unequally shared. So what that means is they're going to be closer to one of the atoms than the other. So it would look like this. So I'll put my two elements here and here. And then I'll put the electrons all the way over here. And then you'll see this a lot. Okay, and so they are sharing, but and that's the mutual attraction to the electrons. So they're sharing, but if you notice, they are intentionally much closer to this element than this one, which actually tells you that this guy is the chlorine and this one is the hydrogen, because if these two electrons are closer to the right, then the right's going to have more negatives, hence the negative charge, making it this side, this one. So, and this one must be the hydrogen because it's not as strong, so the electrons get pulled away further. And so those are the three main type of bonds. The last type that we're going to talk about, and that's it for this, is going to be metallic. So metallic has a unique situation. In metals, what ends up happening is the atoms are all together and nobody wants to gain electrons. So the previous three bonds worked because one atom wanted to gain, one atom wanted to lose, or in the covalent cases, they both want to gain to varying degrees, and so everybody wants to gain something. Well, in the metal situation, nobody wants to gain anything. Gaining is in fact bad, everyone wants to lose. So if everyone has stuff that they want to get rid of and there's no one to take it, what ends up happening is, unfortunately, the atoms just throw away their electrons. They literally just throw it out like it's garbage, and the garbage starts to build up. So now watch. If you've got a bunch of people and they all happen to have, like, they're all sipping coffee in the morning and there's no trash cans to throw out the coffee cups, they all decide I'm just going to throw them on the street. Well, they build up and there'd be coffee cups everywhere. Well, that's what happens here. The electrons literally just start showing up everywhere. They're all over the place. They're between the atoms, they're in the middle of the atoms, they're pretty much everywhere. But here's the problem. The atoms themselves just gave away electrons. So their charge, they were neutral. Now the atoms themselves are positive because they just lost electrons to become stable. And you can see what's going to happen next. As a result, they're now attracted to the electrons that they just threw away to become stable. And since there's no rule saying only one positive can attract to one negative, you end up getting mutual positives, or multiple positives attracted to the exact same negative. And that ends up creating this network which holds the metal together. And it also gives the metal its unique properties. And it looks like that. Now, there's more to it than that, and we'll go a step further. So it turns out my size is not right, meaning metals are typically large atoms. Electrons are microscopically small. If you think about it, if this metal were, let's say, calcium has 20 protons and 20 neutrons. Well, one electron is 2,000 times smaller than a single proton. So that would mean, what is that, 2,040? So that means that if this were a calcium atom, the electron would have to be 80,000 times smaller than that atom. That's not 80,000 times in difference. In other words, if these were the atoms, you still would not be able to see the electrons with the naked eye. That's how small they are. And because they are, and there's a reason I'm saying this, because they are so small, they're actually able to move and trade places with each other. They're also very fast. They're able to move and trade places with each other, almost like a conveyor belt or an escalator for people. And so these electrons are able to move around, which is actually the reason metals conduct electricity, because it's actually the reason metals conduct electricity. It's the reason you can bend a metal without breaking it. It's the reason metals are shiny and not dull and like grayish colored. So it actually makes all of the metals' properties, and we'll go into this a little bit later when we talk about properties, but this is what's called a mobile sea of electrons. And it actually only exists in metallic bonds. And it is the mutual attraction to this mobile sea of electrons that gives metals their properties. It's also what holds metals together. So it is a big deal. And the reason it works is because the electrons are so outrageously small compared to the nuclei of the metal that they're able to move through it. It's like if you were to take it's like if you've ever seen at the beach when the waves crash on the sand, some of the water, recedes back into the ocean, but some of it just kind of disappears right through the sand, and then it will go back down and under. Well, that's the idea. If the sand particles were the metal nuclei, the water itself is so small, the water molecules are so small that they're able to pass by it or through it like there's giant gaps. I mean, obviously we stand on the sand and we don't fall through it, but the electrons or water molecules are so much smaller that they can literally fit between the gaps of the metal or of the atoms, and that's what's really happening here. And so that's everything for single bonds.